Review of the Chem 7L Spring 2020 midterm. Okay. Report the following arithmetic results with the correct number of sig figs. Select one. Okay, so let's look at what we're doing. We're doing multiplication between these three terms. So we have to do these terms each. These are in brackets, so we should do these two together first. But if you realize that they're in brackets and that you still have the same operator outside, you can address them all the same if you want, or independently. It doesn't matter. So let's do the math. Here we have 4 sig figs, which means this answer, whatever this is, should have 4 sig figs. Okay, up top it looks like we have 4 sig figs and 4 sig figs. But do we really? Right? We have 9.253 minus 8.376 yielding 0.877. So in reality, up top is 0.877, that's 3 sig figs. And down the bottom we have 4. Of those two, 3 is smaller, so this only has 3 sig figs. Here, the logarithm of 34.88 has 4 sig figs, plus whatever's before the decimal place if we're going to do multiplication. So it'll actually wind up having 5 numbers, but only 4 sig figs. Regardless, that doesn't matter because 3 is smallest of all of them and wins, which means our answer can only have 3 significant figures, making this 202. Okay, so report the arithmetic results. Very similar problems before, except for we're doing addition. Okay, so let's take a look here. Here we are doing some division, right? And we have 6 sig figs and 5 sig figs, which means this number can only have 5 significant figures. So 1, 2, 3, 4, 5. So we're off at that 5th point there. Okay, what about this one? Well, here, once again, we have some subtraction going on, so let's see what that says. 7.98332 minus 7.98176 means that we have 0.00156. So this is up top is 3 sig figs. And down the bottom, we have 5 sig figs, which means this altogether, whatever this is, which is this, can only have 3 significant figures. 1, 2, 3. So that cuts us off at the 8. Okay. Moving on to the last one. This has 2, 4, 6 significant figures, so 6 sig figs. But when we take the logarithm of it, right, it'll have 2, 4, 6 sig figs. But we also have this in front. So we have 7 numbers, but 6 sig figs altogether. So let's add these together. 3.59358756, where 5 is our significant figure, plus 0.2682555 plus 3 and of course it's the 8, 3.827720703. Altogether that's 7.689593, and our error is coming in at that 3rd decimal place, so that'll round 7.690, because this 5 will cause it to round. So the answer is B. Okay, one more to go. Okay, so we have the logarithm of whatever this number is multiplied by whatever this difference is. Okay, so let's do the left here. Here we have 5 sig figs times 4 sig figs times 6 sig figs. So whatever the logarithm is, we're taking the logarithm of something with 4 sig figs. Okay, so the logarithm of this must have 4 sig figs. So 4 plus the decimal place will be the 5. Okay, so there's 4 sig figs here, but 5 numbers. Here we have some subtraction. We have 9497.32 minus 87.65345 yielding 940. Oh, let's line it up. 9049.666553, meaning we are to this decimal place here. 1, 2, 3, 4, 5, 6 sig figs, right? 6 sig figs times something that has 5, right? So 5 will be our limit here, which means when we do this math, we can only have 5 sig figs, right? 1, 2, 3, 4, 5. Okay. So for the ruler below, how many significant figures should be reported for the measurement of the bar below? Well, let's measure the bar below. Let's take this distance and minus that distance. So we have something that's 11.227, and I'll call the next number 7, 8. Let's go. It's 8 and then 9. And then we'll do the left side, which will be 11.227, and that'll be, I don't know, 13. So that's 6, that's 7.000. So that's 2 sig figs. The answer is 2. Select the definition of significant figures. Okay, all the certain digits that follow the decimal point. That sounds made up. That's awful. No, that's absolutely false. All the certain digits that precede the decimal point. That's silly. That's also false. All the certain digits plus the first uncertain digit. Absolutely. That's the definition of significant figures. But let's continue on and see if there's anything else. All the certain digits plus 2 uncertain digits. That's not true at all. All the certain digits and no uncertain digits. That's silly. Okay. The answer to 5 is C. Oops. Nope. Boom. Okay. Report the following arithmetic with the correct number of sig figs. Select one. Okay. So remember, when we're doing math and you have an answer like this, remember, let's put everything in terms of that number. So we'll have 4.7537, right, times 10 to the minus 11. Okay. So how do we get this to minus 11, right? So we could move this. That would be 14, 13, 12, 11, 10. Right? So 0.000076159 times 10 to the minus 11th. Let's do this one. 13, 12, 11, right? So 0.09147, and then 13, 12, 11, 0.0320, right? And we have the fourth decimal place here. We have the fourth decimal place here. So when we add this all together, 4.87793332. Once again, we're at the fourth decimal place. Will be our answer. That 3 does not cause it to round. There's our answer. Student calculates the average of standard deviation of the pressure of unknown gas as this. The dial and the meter reads on the right. How should the result be presented? Okay, well, let's do it. Rule 1. The error can only be reported with one significant figure unless it begins with a 1 or 2. Oh, this begins with a 1 or 2. So 0.029. But that 7 is going to have it to round. So if that rounds, this goes to 30. And now it's a 3, so we can only keep 1. Rule 2. Your average, your answer, cannot be more precise than your error. So we can only keep to the second decimal place. So 73.2, we have to round it, 8. Number 3, are we doing better than the instrument? Well, let's see what the instrument is. Let's pick a point. Boom. I'm just going to pick any point. What is that number? Well, that would be 80. 1, 2, 0.3, right? Maybe, I don't know, 0.4, 0.3. By doing this, by putting that number on there, I can show you that, right, we have a certainty where there's a line for the 80s, there's a line for the ones, and the first thing there's not a line for, our first uncertain digit, is the first decimal point. So that means our instrument error is plus or minus 0.1. So what is bigger? Plus or minus 0.1 or plus or minus 0.03? It's plus or minus 0.1. So we have to use the plus or minus 0.1, and then we'll use 73.3 because that has to round. D. Student calculates the average of standard deviation for pH of an unknown acid as 4.6 blah 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 plus or minus 0.839526. The pH meter shows 2 decimal places. How should the result be presented? Rule 1. Error can only be reported with 1 sig fig unless begins with the 1 or 2. Does not begin with the 1 or 2. 0.8 is my error. Rule 2. I must match. My answer can't be more precise than my error, so I have to match it. 4.6. Am I doing better than my instrument? Well, here's a picture of my instrument. My instrument can go plus or minus 0.1. What's bigger, plus or minus 0.1 or plus or minus 0.8? Plus or minus 0.8 is bigger. Boom. Answer is B. A student calculates the average of standard deviation for a pH of an unknown acid as 12.63 plus or minus 0.00366942. The pH meter shows 3 decimal places. How should the result be presented? Rule 1. I can only report the error with 1 sig fig unless it begins with a 1 or 2. This is good. It does not, so 0, 0, that 3 will round to a 4. Rule 2. My answer cannot be more precise than my error. I can have to go to the third decimal place, and that will round. 12.638. Am I doing more precise than my instrument? My instrument goes to the third decimal place, 0.001. What's bigger, 0.001 or 0.004? 0.004 is, ergo, that's my answer. The answer for 9 is D. A student measures the pH of an unknown solution 3 times and obtains the average of 6.2731 and a standard deviation of 0. The pH meter used is shown below. How should I report this result? Well, my standard deviation can never be 0, right? That's an artifact of having a small n, right? They're all the same. So we have to set it at the minimum of our instrument. Our instrument is 0.1, which means our answer has to be 0.1 and it will round, right? So 10, the answer is A. An acid has a Ka value of 4.649362 times 10 to the minus 8. The corresponding pKa is shown on your calculator as 7.3326066638. Report this pK with the correct number of sig figs. Okay, so this is a regular number, and we have 1, 2, 3, 4, 5, 6, 7 sig figs, which means we have to have 7 sig figs to the right of the decimal point. So let's see which answer has 7. Let's start with the longest one. 1, 2, 3, 4, 5, 6, 7. Bingo, we found it. Everything else is too short. Answer is C, right? Because this is a logarithm, right? Because the minus log of the Ka equals the pKa. The pKa of an acid is reported as 4.3. The corresponding Ka shown in your calculator is 5.01187 times 10 to the minus 5. Report this concentration with the correct number of sig figs. Remember, pKa is the negative log. This is a logarithm, so you only have sig figs to the right of the decimal place. That has 1 sig fig, which means our answer can only have 1 sig fig. 5 times 10 to the 5th. The student measures the mass of a precipitate for 6 trials using the balance shown below and calculates the average is 3.438637 grams and the sample standard deviation is 0.0439682 grams. How should the student report the results? Rule 1. The error must be reported with 1 sig fig unless it begins with a 1 or 2. This, however, does not. And because it's a 3 there, it will not round. 2. the number or average or result cannot be more precise than the error, so we have to go to the second decimal place, and that 8 will cause it to round, so 3.44. 3. We can't do better than our instrument. There's our instrument. Our instrument indicates 0.01. What's bigger, 0.04 or 0.01? 0.04 is bigger. That is our answer. So B. You measure the mass of 3 aliquots of DI water using a balance that has 4 decimal places and get the following masses. You calculate the number of moles in each aliquot using a calculator. The calculation for the first sample and calculator output are as follows. The average number of moles and sample standard deviation for all 3 aliquots show up on your calculator as 0.3166456 plus or minus 0.00120626 moles. How should we report resulted? Select one. Rule number 1. Report the error with one sig fig unless it begins with a 1 or 2. This begins with a 1 or 2, and it does not round. Rule 2. Report your answer with no higher precision than the error. So we have 4 decimal places. That 4 will not cause it to round, so we have 0.3166. Rule 3. Are we doing better than our instrument? Well, let's find out. Here's a sample calculation. This is from our scale with 4 decimal places, which means the average error from our scale is in the 4th decimal place here. Our error from our grams of water is also in the 4th decimal place, right? This is an infinite number of sig figs because it's 1. So we can only have 4 sig figs in our answer, which means our error will be in the 4th decimal place. So our instrument response for this happens to be in the 4th decimal place. Which one is bigger, right? A 12 or a 1? Right? It winds up it's the 12, and our answer stays, so our answer is C. You measure 3 aliquots of DI water using a balance. And it has 4 decimal places, and you get the masses are the following. You calculate the number of moles each aliquot using a calculator. The calculation for your first sample calculation output R is this. The average number of moles and sample standard deviation from all 3 aliquots shows up on your calculator as 0.55487236 plus or minus 0.000959306. Okay, rule number 1. Does it begin with a 1 or 2? No, then I must report it with 1 sig fig. So plus or minus 0.0009. But that 5 will have it round up. So if it rounds up, and now begins with a 1, I must keep 2 sig figs. It begins with a 1. Rule number 2, I have to report my answer, right, with the same precision. And also, once again, that one rounds up. Okay, rule 3, am I doing better than my instrument? I have 5 sig figs. Here I have 3 sig figs, which means my error is in my 3rd decimal place. Oh, sorry. I have 4 sig figs. Let's see. Brian can't count. 4 sig figs, so once again, it's in my 4th decimal place. So what's bigger? Right? 10 or 1? Right? It's the 10, so this is my answer. 5549. That would be answer D. Okay, a student measures the mass precipitate using 3 different balances that show 5, 3, and 2 decimal places and record the following values. 128.43173, 130.626, and 126.72. The average is calculated. The result from the calculator is given. Report the average with the correct number of sig figs. Hopefully you're C. If you're adding these two, you have 2 decimal places. 130 point, there's 2 ways to solve this. 28.43178. When you add them all together, you can't do better than that 2nd decimal place, right? And then when you divide that number by 3, right, which is an integer, so it's infinite sig figs, right, you'll have to that 2nd decimal place is the best you can do because this balance sets it. Or you can just say, hey, this balance sets it for everyone because Remember, these are all in grams, and my answer is in grams. I'm not going grams to moles or grams to molarity or anything. Okay, so the answer is E. You measure the temperature of your solution 4 times and calculate the average and standard deviation as 32.8 plus or minus 0.13. You later find out that your thermometer is not calibrated and is reading too high by 6 degrees. How does this new information affect your average and standard deviation? Okay. Well, let's think about it. We have some average, right? Our average is this, our 32.8, and our standard deviation is 1.3. So what's going to happen to our average, right? If we are too high, our average should drop by exactly 6.0, right? So we should go from a 32.8, we should drop 6 to get to 26.8. Okay, but what does this do to our standard deviation? Okay, right? This is a systematic error. Should it affect the random error? And the answer is no. Okay, let's prove that to ourselves, right? How do we do our standard deviation, right? In class, right? We have the value minus the average divided by n minus 1 square root, and that gives us our standard deviation. Okay, so let's take a look at this. Okay, let's take a look at this equation and figure out how S will change. Our n, right, we still have 4 samples, so this n and n minus 1 does not change. So let's not worry about that for now, okay? Let's look at x minus x bar, our number minus our average. So let's say we have 3 values. I don't know what they are. Let's say it's, we're going to do 3 in here for fun. Actually, I can actually calculate it. It'll be 31.5, 32.8, and 11, carry 1, 34.1. These 3 values will give you this average and that standard deviation. Okay? So each one of these, right? Let's look at the average. The average would be 32.8. So 32.8 minus that would be 0. Minus 32.8 equals minus 1.3. And minus 32.8 equals 1.3. Okay, so this would be 1.3, right, squared, 0, 1.3. Okay, but let's do this. What would the values be if we dropped everything by 6 degrees? So if this was really, if we're really measuring 26.8, and we dropped this by 6 degrees, what would it be? 20.8, right? And then we raised it by 6 degrees, right? Oh, didn't do that right. So 31.5 minus 6, 2. $11. 25.5. And then this one would be okay. So the average is 26.8. That's the average. So if when we do this term here, it'd be 0. And then we minus 26.8 here, it'll be minus 1.3. And when we minus 26.8 here, it'll be 1.3, which means this term doesn't change either. So if the numerator and denominator do not change, S does not change. S is your standard deviation is unaffected. Okay, you can prove this yourself just by a quick little mathematical inspection. So let's take a look. A, the average is actually 26.8, but the standard deviation is unaffected. That would be the correct answer. The standard deviation is actually 6 degrees C, but the average is unaffected. That's awful. The standard deviation is actually 7.3, but the average is unaffected. No. The average is actually 38.8, but the standard deviation is unaffected. No. and the average and standard deviation both affected should be recalculated with the correct values of temperature. No, they're not both affected, right? So no. 17, the answer is A. 18, select all statements that are false. Random error shift results in both directions. That is true. Systematic errors, in theory, can be identified. Yes, you use a standard. True. Random errors always have a Gaussian distribution. Yes, true, Gaussian. Repetition of measurements will not reveal systematic error. That is, of course, true. If you keep measuring with a short measuring tape, it won't work. Random errors can be made smaller by increasing the number of trials. Absolutely false. It just tells you what the number is. It doesn't ever make it smaller. So the only answer that is false on 18 is E. After 49th trial, the average mass delivered from a pipette is 32.0 grams with a standard deviation of 2.3. If you perform a 50th trial, what is the probability that the mass will be lower than 27.8 or greater than 34.3? Well, let's do a standard deviation curve. Let's get our little 32 on the map. Let's do the first standard deviation. That's really asymmetric. So we have, this would be 34.3. So 1 sigma. And let's take away 2 and then 0.3. So this would be what? 29.7. That's minus 1 sigma. And let's do another one. Let's minus another 2.3, and we get 27.4. So this is 2 sigma. So we want to know everything under the curve this way and everything under the curve that way. Okay, let's break this up into 2 problems. One is 2 sigma to the left, and one is 1 sigma to the right. Okay, let's do the 2 sigma case. 1 sigma, 2 sigma, right? So everything underneath 2 sigma is 95%, right? Which means that plus this is 5%. So this is 2.5, and that's 2.5. We only want this area, so we have 2.5% chance. Let's do the 1 sigma case, right? Under 1 sigma, right, in here we have 68%, right? Which leaves 32 on these 2 sides, which means 16 and 16. And we want this area. So we have 16 to the right, and 2.5 to the left is 18.5. Let's see. Select a true statement about RSD. Okay, A, more than one statement is true. We actually have to go through them before we can select that one. The sample RSD equals the population RSD when the sample average equals the population average. Well, we should know that's false, right? Because we actually saw that when we did both jockeys and NBA players, right? The average wound up being the population average, right? That worked out pretty well, but yet the standard deviation was much larger than the population standard deviation, right? So we really don't know anything. We can't say much about where averages equal averages, because the average, once again, can go back and forth across that population average multiple times before it settles on it at the end. So this is false. It's very misleading. It's very tricky, but it's absolutely false. You can have... for example, if we had everyone in the class stand up that was 5'8", that's the population average. What's our standard deviation at that point? It's not going to be like the rest of the country, which means our RSD will be wrong. They won't match. So this is absolutely false. None of the statements are correct. We've got to come back to those two. The sample RSD approaches the population RSD when the sample size approaches the population size. Ooh. This has text we're interested in, right? Sample size, n, approaches the population size, capital N. So we know 2 things. When n approaches capital N, we only know 2 things. S approaches sigma, and x bar, right, approaches mu. right? We don't talk about RSD, but let's think about this. What would our sample RSD be? Our sample RSD is really S over X bar, and our population RSD is sigma over mu, right? Both of them times 100, right? And S goes to sigma and X bar goes to mu as N approaches capital N. So this is absolutely true. The components that make up RSD are the two components that do approach each other when the sample size approaches the population size. So this is absolutely true. The sample RSD provides information about the accuracy of the measurements. No, remember, RSD provides information on precision. So none of the statements for this question are correct. No, we do have a good one. And more than one is true. Nope, that is also false. So it's just D. 20 is D. How should we report an average and its corresponding standard deviation? Select one. The average and standard deviation should have the same number of sig figs as the number of decimal places. That's awful, right? We know that won't happen because when we report our standard deviation, we leave it with one sig fig most often than not. B, the average should be reported with one significant figure unless it begins with a 1 or 2. Then it is reported with 2. Kind of true, right? You should report the error with one significant figure, but not the average, right? The error, yes, not the average. Sneaky, sneaky. Okay. The average should be reported to the same decimal place precision as the standard deviation. Exactly. So if your standard deviation is to the second decimal place, your average should be reported to that too. This is true, right? Directly from the definition in the slide. The average and standard deviation should have the same number of significant figures. That's false, right? Not the same number of sig figs. None of the statements for this correction are correct. Nope, that's also false because we do have a true one. 21 is C. Nope. 22. Select all statements that are true. 1 to 5 answers. The percent error provides information on the relative accuracy of one measurement to another measurement. Yes, this is exactly what we did in experiment 1. Remember, we compared our graduated cylinder to our volumetric pipette to the beaker. We compared accuracy from a set of different measurements to measurement to see what had higher accuracy. Absolutely true. We also talked about this in class, right? Systematic errors contribute to the percent error. Yes, right? Systematic error is defined by, right, the percent error. True. Random error is revealed with repetition of measurements. Yes, you do a bunch of measurements, you're able to get the standard deviation. It tells you what the number is. It doesn't make it smaller. It doesn't make it bigger. It just reveals it. It tells you what it is. Systematic error can sometimes be revealed by using a standard. Yes, right? When you have that shrunken meters, that ruler, right? It was cloth and it was shrunk, remember? You can test it with a standard. You can buy a standardized ruler and then tell that's where your problem is. So sometimes, yes, it can be revealed by using a standard. Random errors reflect statistical fluctuations associated with the measurement. Absolutely. They do reflect those statistical fluctuations with the measurement. So for 22, the answer was all of them. 23. You're performing a standardization and titration to determine the molecular weight of an unknown acid. The calculation for a representative trial is shown below. When applying the third rule of reporting errors, what should we consider to be the instrument error? Select one. Well, let's do the math. Luckily, it's all multiplication, so we just have to track the number of sig figs. Let's see, here we have 6 sig figs, here we have 5 sig figs, here we have 4 sig figs, which means this only can have 4 sig figs. It's continued down here, right? There it is. So there's your 4th sig fig, right? So this has 4 sig figs. This has 3 sig figs. This has 4 sig figs. Now 3 is the lowest. So we can only have 3 sig figs, which means our error will be in that 3rd sig fig spot. So it's plus or minus 1. What is the correct reading for the burette on the right? Select one. Okay, Is it greater than 62? Yes. Is it less than 63? Yes. So, I mean, not 62, 6.2. So it's definitely a 6.2. Okay, great. So 6.2, and this is 0.01, 0.02, 0.03. Okay, so you could call it 2 or 3. It's up to you. Maybe we'll call it 2 first. And then we'll have to estimate the next number in here, okay? I'm going to say it's 9. Okay, so we have to have 3 places, right? It has to be a 6.2, and it has to have 3 decimal places. 6.2, 6.2, these are not 6.2. 3 decimal places, well, maybe someone read it differently, right? So it cannot ever be this number. It does not have the right precision. This is a viable reading of that burette, so the answer is B. You get a new job in a deli weighing cold cuts, potato salad, and other food for customers. Last Thursday, you placed a container of pickled green beans on the scale/balance. You take the container off the scale before you print the price sticker for the customer, so you must place it back on the scale so you can print the price sticker. You notice that the price in the computer is less now than it was the first time you weighed it. Remember, right? That price is reflective in its mass, right? The heavier your pickled green beans are, the more you have to pay for them. You lift the container on and off the scale to see the price goes up sometimes when you put it back on the scale, and other times it goes down. You hand the delicious green beans to a confused customer and think about what you observed. Okay, the scale balance has low accuracy. We have no information on accuracy of this system, so no, we can't say it has low accuracy because we don't even give you a number to tell you, and what it should be. So absolutely no. The scale balance is not properly calibrated. Once again, that's an identical question as A. It has low accuracy. You have no information on that. You observe fluctuations arising from systematic error. Systematic error only goes one direction, right? And we see here, but sometimes the price goes down and sometimes the price goes up. So our error is going both up and down. So it is not systematic. You observe fluctuations that arise from random error. Yes, right? We're seeing fluctuations in the mass going up and down, right? It's bouncing around. That's a statistical fluctuation. That's really the definition of our random error. Lastly, the scale is accurate and has high precision. We have no information on that either, right? So really, we are just observing fluctuations arising from the random error.